So I want you to imagine spending $10 million to hire these elite PhDs in industrial engineering.
Oh, right. Big guns.
Exactly. You bring them in to build this state-of-the-art, fully automated robotic production facility. I mean, you spare absolutely no expense.
Naturally.
And yet, 6 months after the ribbon-cutting ceremony, you walk down onto the factory floor, and what do you see? This exact same brilliant scientist, covered in grease, manually pulling jammed cardboard out of a, $50 sensor assembly.
Yeah, it is painfully common.
Why does this happen? Well, it's because of a fundamental law of physics that, honestly, most managers completely ignore.
It's a scenario that plays out in almost every industry. Across the globe, really.
Sure.
We kind of just assume that, throwing massive amounts of capital and brilliant minds at a complex process is just going to automatically yield a smooth operation.
Just buy your way out of it.
Right, exactly. But what those PhDs discover, and usually the hard way, is that systems just do not care about your budget. They don't care about your academic credentials. Systems are governed by the rigid mathematics of flow.
Welcome to the Deep Dive. Today, we are entirely focused on giving you a practical, step-by-step framework to identify and resolve operational bottlenecks.
And this is so crucial.
It really is, because we're tackling this due to a universal frustration. If you've ever managed a complex process, whether you run a massive manufacturing plant, a software development team, or honestly even just a busy restaurant kitchen, you have felt this.
Oh, absolutely. Everyone knows the feeling.
You spend weeks agonizing over this one massive choke point in your workflow. You finally figure it out, right? You implement the fix, you celebrate the big victory, and literally the very next day, a brand new bottleneck pops up just 10 yards down the line. It is maddening.
It feels like playing an endless game of operational whack-a-mole.
Yes. Whack-a-mole.
Yeah. You smash one problem down with a mallet, and another one just immediately pops up to take its place. And if you don't understand the underlying mechanics of what is actually happening there, you're just left standing there holding the mallet.
Just wondering if you're doomed to fight fires forever.
Right. So our goal today is to transition you out of that reactive firefighting mode. We really want to equip you to become the quiet architect of your systems.
I love that phrase, the quiet architect. So to get us there, we are synthesizing an incredible stack of sources today. On one hand, we're looking at deep tech architectural frameworks from Prasad Bond.
Which is fantastic material.
It is, specifically a piece called The Physics of Deliberate Constraint Engineering. But, theory only gets you so far.
Right, you need the practical application.
Exactly. So we are pairing that high-level physics with real, gritty, problem-solving threads from frontline manufacturing operators, factory owners, and continuous improvement engineers, the people in the trenches.
And that contrast between the high-level theory and the messy reality of the factory floor is where the best insights live. I mean, the theory tells you what the math says should happen.
And the operators tell you what happens when humans actually touch the machines.
Exactly.
Okay, let's unpack this. Why does fixing our biggest problem usually feel like we haven't made any progress at all? Why is it that when we clear a massive production limit, the total production volume often just remains completely unchanged?
Well, it's because of the fundamental physics of a continuous flow system. By definition, a continuous flow system is always limited by a bottleneck. Always.
Right. Always.
Always. It's a hard mathematical limit. You can think of it as a law of physics for operations.
Okay, so give me a visual for that.
Think of water flowing through a series of pipes of different diameters. The total amount of water that can exit the final pipe is entirely dictated by the single narrowest pipe in the entire sequence.
So it is literally impossible to have a system without a bottleneck. If you have a system, something is limiting it.
Inherently, yes. And this is where leadership frequently misinterprets plant floor physics. Because when you swap out that narrowest pipe for a wider one, when you clear that primary restriction, the system doesn't suddenly become limitless.
Right, it doesn't just infinitely expand.
No, the title of narrowest pipe simply transfers to the next narrowest section of the plumbing. The next slowest process naturally and automatically inherits the crown.
Oh, wow. So if you're listening to this and you've ever been in charge of a process overhaul, you are probably nodding along right now.
Because the assumption is always, hey, we just dropped $100,000 to clear this bottleneck. Why aren't we producing 20% more?
Right. But if your old bottleneck was limiting you to, say, 50 units an hour, and your second slowest step down the line can only handle 52 units an hour.
Fixing the first one only buys you 2 extra units before you hit the new wall.
That is wild.
And the tragic part of this dynamic is that continuous improvement engineers, or those frontline managers, they often take the blame for the stalled throughput.
Oh, I'm sure.
Because the executive team sees this massive capital investment to fix the first problem, right?
Oh.
But they don't see a proportional massive increase in total output.
So they just assume the engineers failed.
Exactly. Or they assume the new bottleneck is a brand new failure of management, rather than recognizing it as the natural, mathematically inevitable emergence of the next limit.
I was actually reading through the source threads, and there's a specific operator who shared this exact frustration. They said they just kept requisitioning new tools, new software, just hoping it would fix things.
And let me guess, the same operational issues kept showing up.
Yes, they fix one bottleneck, another pops up.
They were starting to wonder if the problem wasn't the tools at all, but the foundational way their workflow is designed. Like, is it possible we're just buying the wrong tools?
That operator was actually having a massive breakthrough realization. I mean, if bottlenecks are an inescapable law of physics, then our traditional method of just throwing money and new tools at them is completely backwards.
We're basically just treating the symptoms. Right. You cannot buy your way out of a bottleneck if you don't understand the entire workflow. Throwing a faster machine into a broken sequence is, well, it's like putting a Ferrari engine into a golf cart.
You aren't going to win the race, you're just going to crash faster.
Exactly.
That analogy actually leads us perfectly into what the sources call the fallacy of localized optimization. And to understand this, we need to talk about the law of constraints.
Right. So the law of constraints states that your total system output is strictly equal to the output of the single slowest node, period.
Period.
It's just the slowest node.
Yes. Nothing you do anywhere else in the system can increase your total output unless it directly increases the output of that specific single slowest node.
That sounds incredibly simple on paper, like it makes total logical sense. But in reality, larger organizations mess this up constantly.
They really do.
And the sources point to a very specific reason why we fail at this. It's the hidden incentives built into middle management. Oh, this is a fascinating organizational psychology issue. Middle management is almost universally incentivized by localized efficiency metrics.
Let's create a scenario to illustrate this for the listener. Imagine a factory with 3 machines in a row. You've got machine A, machine B, and machine C.
Okay, pretty standard setup.
Right. Now, the manager in charge of machine B realizes that with a little tweaking, he can get his machine to run 15% faster. He pitches the idea, does the work, hits the metric, and, probably gets a nice year-end bonus for his initiative.
He looks like a hero. But let's apply the law of constraints to that scenario. Let's say machine B is not the ultimate system bottleneck.
Okay, so it's just a regular step in the middle.
Right. Let's say machine C, the final step down the line, is the actual slowest node. By optimizing machine B, that manager mathematically guaranteed 0 improvement in total systemic output.
Wait, 0?
0. The manager gets a bonus for a 15% localized improvement. But the factory as a whole doesn't produce a single extra finished product to sell to a customer.
It reminds me of a relay race. Like, it does not matter if your first runner breaks the world record for their leg of the race if your anchor runner is just walking.
That's a perfect analogy.
You don't give the first runner a gold medal for a localized victory while the entire team loses the race. But in corporate environments, we literally hand out those gold medals every single day.
We do. And it gets much worse than just a useless bonus, honestly.
How so?
That localized optimization actually causes active financial harm to the company through what the sources call capital leakage.
Okay, here's where it gets really interesting.
Yeah.
Walk us through the physical reality of capital leakage. What happens to all that money and effort when machine B speeds up?
Well, think about it. If machine B is running 15% faster, but machine C hasn't changed its speed at all, what is machine B actually doing?
It's just making more stuff that C can't handle.
Exactly. It is just taking raw materials and turning them into half-finished goods 15% faster, only for them to sit in a giant pile right in front of machine C.
So you're just building work-in-progress inventory YIP at a much faster rate right before the actual bottleneck.
Yes, and we have to be very clear about what WIP inventory actually is. It is trapped cash.
Trapped cash.
It is money burning a hole on your factory floor. You've already spent the capital to buy the raw materials. You've already paid for the labor and the electricity to process those materials at machine B.
Right.
But because machine C cannot process them fast enough, those goods cannot be finished, they cannot be shipped, and they cannot be sold.
Wow, so that cache is literally locked inside a physical pile of half-completed widgets just taking up floor space.
Precisely. You are spending massive amounts of capital just to pile up inventory faster without producing more finished goods.
Not to mention, you now have to pay to store that WIP. You are taking up valuable square footage. You might even have to, like, rent additional warehouse space just to hold the very inventory you paid your manager a bonus to create.
It is the ultimate illusion of productivity.
Yeah.
I mean, everyone feels busy, the machines are humming, the local metrics look amazing on a spreadsheet.
But the bottom line is completely flat.
Right. And what's truly fascinating here is how deeply ingrained this fallacy is in corporate culture. From business school onward, we are taught to optimize everything.
Right, idle hands are the devil's workshop and all that.
Exactly. We are taught that a machine sitting idle is a waste of money, that an employee standing still is a failure of management. But the physics of flow tell us the exact opposite.
Wait, the opposite.
Yes. If you have a non-constraint machine, making it work at 100% capacity is actively detrimental to the financial health of the business.
Okay, so to stop wasting capital on these localized illusions, we really have to cure our own operational blindness. We have to be able to see the entire board, not just individual machines.
Yes, and that requires a radical level of visibility. You cannot manage what you cannot see.
So when that frustrated operator and the sources complained that fixing one bottleneck just revealed another, the advice they got from the continuous improvement community was absolutely unanimous.
What do they tell?
They said you have to map the full workflow before you touch a single machine. You have to distinguish between the visible symptoms that annoy you and the actual root causes that are throttling your system.
And the gold standard tool for achieving this visibility, according to the operational frameworks, is value stream mapping.
Right, value stream mapping, VSM. Now, my understanding is this isn't just drawing a quick flow chart on a whiteboard.
Oh, definitely not. It is a highly specific method used to visualize the entire process, from the exact moment a customer places an order to the moment they receive the product.
And its primary function is to brutally separate value-added activities from non-value-added activities.
Brutally is the right word.
Let's break those terms down for the listener because they are so foundational to this. What is the actual difference between a value-added activity and a non-value-added activity? Because, I imagine to a floor manager, everything feels necessary.
It does. But the sources define a value-added activity through a very strict lens. It is an action that the customer is actually willing to pay for.
Okay, so what does that look like physically?
It is an action that physically or chemically transforms the product closer to its final desired state. The core concept here is the unit process.
Give me a tangible example of a unit process. What are we looking for on the floor?
Fastening a screw into a subassembly, cutting a piece of raw wood to the correct dimensions, injecting hot plastic into a mold. Those are unit processes.
Because the product is physically changing.
Exactly. The molecular state or physical assembling of the product has been altered in a way the customer desires. That is value added. Everything else, and I mean literally everything else, is technically non-value-added waste.
Wait, everything else. So moving material around the floor, inspecting parts for quality, storing inventory in a rack, even an employee walking from one workstation to another to grab a wrench. All of that is non-value-added.
Yes. From the perspective of pure value stream physics, all of that is waste.
That's a tough pill to swallow.
It is. Now, some of it is necessary waste.
Yeah.
You obviously have to inspect parts to ensure quality, and you do have to move materials from station A to station B.
Right.
But the customer does not care that your employee had to walk 50 feet to get a tool. The customer is not paying you to move a box across a room. They're only paying for the fastened screw.
So when you create your value stream map, your goal is to lay out this brutal reality. You identify every single step, and you realize that perhaps only 10% of your process involves the actual unit process, while 90% involves waiting, moving, and storing.
That is precisely the point of the exercise. Once you have that map, you aggressively redesign the physical work environment to favor the value-added unit process.
You want to eliminate as much of the non-value-added movement as geometrically possible.
Exactly.
And the sources offer some incredibly pragmatic advice on this. One continuous improvement engineer suggested using gravity to assist material handling wherever possible.
I love that one. It's so elegant.
It really is. Just literally redesigning the line so that when a part is finished at one station, it simply slides down a physical ramp to the next station instead of paying a human being to pick it up, put it on a cart, and push it 20 feet.
It sounds almost insultingly simple.
Right, but when you scale that out across 10,000 parts a day, the time and labor savings are astronomical.
And to find those specific opportunities, you really have to pair your value stream map with rigorous cycle time analysis. You have to understand exactly how long every single node in your process takes.
How does a manager actually conduct a cycle time analysis in the real world? Are we just talking about standing out there on the floor with a stopwatch?
Honestly, it often starts exactly like that. You stand on the floor under normal operating conditions, and you time how long it takes a specific workstation to complete one full cycle of their task.
Just literally watching and timing.
Yeah. You do this repeatedly to find an average. You map the cycle times of every node, and once you have that data, you sort your process steps from the worst offender, the slowest time, to the least worst.
And this is critical because human nature makes us want to fix the problem that is loudest, right? Or the most annoying, or the easiest to reach.
Absolutely.
But the math tells us we have to tackle the mathematically worst offender first, regardless of how we feel about it.
You must work a solution for the worst ones first. And this sorting process actually provides a built-in diagnostic for your map.
How so?
If you fix a bottleneck, and a new one appears in an area you didn't expect, or it appears out of order from your sorted list, that is a massive red flag.
Oh, because it means your data was wrong.
Exactly. It means your initial mapping process was flawed. You missed a hidden variable, or you miscalculated a cycle time.
But let's inject a dose of messy reality into this theory, because the sources give us a fantastic real-world case study here.
Let's hear it.
There is a factory owner who posted anonymously asking for help. They run a manufacturing facility in China, pulling in $20 million in revenue a year, and they're taking home about $4 to $5 million in profit.
Which, as many people in the continuous improvement community quickly pointed out, is an incredibly strong position.
Yeah, a 20 to 25% profit margin in physical manufacturing is stellar. One commenter literally told him he was printing cash and warned him not to kill the golden goose.
That's great advice, honestly.
Right, but the owner is feeling the squeeze of rising operational costs. He has 400 plus employees. His labor costs are extremely high because he manufactures multiple different products that require what he called loads of hands.
Okay.
He doesn't have the massive volume of a single identical product or the simplicity to just buy robots and fully automate the whole floor.
This is a classic complex scenario. Flexible automation robots that can adapt to high-mix, low-volume production is astronomically expensive.
Because robots like doing one thing.
Right. Robots are brilliant at doing the exact same motion a million times.
Yeah.
They are terrible at doing 50 different complex tasks 1,000 times each. That is exactly why this owner still relies on human labor.
Makes sense.
And when you have high labor costs and high product variability, human motion is where your money is silently bleeding out.
So let's say this owner takes our advice. He maps the floor. He finds the massive amounts of non-value-added activity, people walking to get tools, people waiting for materials, over-processing things. He finds the true root cause, and he knows exactly where his worst mathematical bottleneck is. What's next?
Well, what would you do?
I mean, my instinct, and I think the instinct of 99% of managers, is to just fix that bottleneck, to make it faster, widen the pipe.
And that deeply ingrained instinct is exactly what traps us in the never-ending whack-a-mole game. The goal, according to the deep tech architectural framework from Prasad Bond, is not to simply fix the bottleneck.
Okay, you're going to have to explain this carefully. If the goal isn't to fix the bottleneck, what is the goal?
The goal is to deliberately choose where the bottleneck lives.
Wait, you want to intentionally design a bottleneck into the system?
Yes. High-performing facilities understand that eliminating all bottlenecks is a mathematical impossibility. A constraint will always exist.
Right, the pipes.
Exactly. Therefore, they design their production lines so that their most expensive or most scarce resource is the deliberate constraint. They intentionally build the bottleneck around their most valuable asset.
This is a massive paradigm shift. You are actively deciding what holds your entire business back. Why on earth would you choose to limit your own system?
Because of a concept known as the depreciation rule.
The depreciation rule.
This rule states that your highest depreciation asset, the specific machine or resource that costs you the most capital to acquire and maintain, must have the highest utilization rate of anything in your building.
Okay.
You must prioritize every fix and every process change based entirely on how it impacts the overall system throughput, and your most expensive asset is what should dictate that throughput.
Okay, I really want to explore this deeply because it feels so counterintuitive. Let's use the bottling plant example from the sources because I think it perfectly illustrates the mechanical reality of this.
It is a brilliant example. So imagine you run a massive bottling plant. You have a central filler machine. This is the complex piece of engineering that actually injects the liquid into the bottles.
Right.
It costs you $1 million to purchase and install. It is your heaviest capital expenditure by far, your $1 million baby. And according to the manufacturer, it operates at a maximum safe speed of 30 units per minute.
Okay, so I know my filler runs at 30 units a minute, and because it's my most expensive asset, I want it to be my system constraint.
Correct. Now, consider the rest of your factory floor. You have machines upstream of the filler like the uprighters. These take jumbled empty bottles from a bin and stand them up on a conveyor belt.
So they feed the filler.
Yes. And you have machines downstream like the cappers that screw the lids on and the packagers that put the bottles into cardboard boxes.
Okay, so if my filler runs at 30 units per minute, my immediate managerial instinct is to go out and buy uprighters and cappers that also run at exactly 30 units per minute.
Why?
Because why wouldn't I? It seems like perfect balance, no wasted capacity, perfect localized efficiency, everyone working at the exact same speed.
That is the localized optimization fallacy striking again, and it will destroy your throughput.
Wow, really?
Think about it. If every single machine on your line runs at exactly 30 units per minute, you've created an incredibly brittle, fragile system. Think about the physics of it. If there is a tiny hiccup anywhere in the system, let's say a plastic bottle gets jammed in the upstream uprighter for just 10 seconds.
The uprighter starves.
And because the uprighter was only producing exactly enough bottles to feed the filler immediately runs out of bottles.
Oh, I see.
Your $1 million machine grinds to a halt. It is starved. Or imagine a misaligned cap causes a 5-second delay in the downstream packager.
Then the finished bottles back up on the conveyor.
And they block the exit of the filler. Your $1 million machine has to stop because it cannot eject its product.
Wow.
In a perfectly balanced line, the downtime of any single cheap machine instantly becomes the downtime of your most expensive asset.
Wait, I see where this is going. If the uprighter breaks, the filler stops. If the capper breaks, the filler stops. You are literally letting $50,000 secondary machines dictate the uptime of a $1 million primary asset. That is insane.
It is.
So how do we avoid that?
You intentionally overdimension the secondary assets.
Overdimension. You mean buy machines that are deliberately too fast for the system?
Yes. If your $1 million filler operates at 30 units per minute, your cheap upstream uprighters must be designed and purchased to run at, say, 40 units per minute. Your downstream cappers must run at 45 units per minute.
I'm going to push back on this hard because if I'm a plant manager and I pitch this to my CFO, I am going to get fired.
Do you think so?
You are telling me to spend company capital to buy excess capacity on secondary machines, knowing full well they will never be fully utilized. You're telling me to buy an uprighter that can do 40 a minute, knowing the filler can only take 30.
Right.
That uprighter is going to be sitting idle for 25% of its shift. How do you defend that to a board of directors?
You defend it by explaining that you are sacrificing the localized efficiency of a cheap machine to guarantee 100% utilization of the expensive machine.
Okay, say more about that.
You are overdimensioning the surrounding assets to guarantee that the primary asset never starves and is never blocked.
Yeah.
Because the uprighter runs at 40 units a minute, it easily builds a buffer of empty bottles right in front of the filler.
Ah, a buffer.
Yes. So if the uprighter jams and goes down for 30 seconds, the filler doesn't even notice. It just keeps pulling from the buffer. The $1 million machine keeps running. The same goes for the downstream capper. Because it runs at 45 units a minute, it clears finished bottles away from the filler faster than the filler can produce them. The conveyor is always empty. The filler is never blocked.
So the uprighter might have to pause for a few seconds every minute because it's working too fast and the buffer is full, but who cares?
Who cares? It's a cheap machine. Its downtime is financially irrelevant compared to the downtime of the filler.
Exactly. You are forcing the filler to act as the permanent, unmovable system limit. You engineer the constraint deliberately.
And if you do this, your continuous improvement engineers will never be blamed for stalled throughput again, because the throughput is explicitly dictated by the known, protected, maximum capacity of your primary asset.
That is a staggering realization. It really reframes the whole picture. But, we have to address the human element here.
Always the tricky part.
Right, because you can engineer the perfect machine constraints. You can map the floor, you can
Okay.
intentionally overdimension the uprights to protect the filler. But machines don't run themselves. They are maintained, operated, and fed by human beings, and humans are messy.
Very messy. Human variability will degrade even the most perfectly engineered system. This goes right back to our factory owner with the $20 million in revenue and 400 employees.
With loads of hands.
Right. When you have that many individual human hands touching the product, even microscopic motion inefficiencies scale into massive financial losses.
I mean, if an employee takes one unnecessary step to grab a tool, it takes maybe 2 seconds. It feels like absolutely nothing.
But if they do that 100 times a day, across 400 employees, over 250 working days a year,
The lost time, the lost capacity is astronomical.
which is exactly why the continuous improvement community in the sources heavily emphasized implementing standardized training. You have to reduce human errors and variability.
Yeah, because you cannot optimize a process that is performed differently by every single operator.
Exactly. And one commenter provided some incredibly practical, low-tech, high-impact strategies that any facility could implement tomorrow.
I loved these suggestions because they don't require like million-dollar software installations. One of the biggest recommendations was cross-training employees.
Cross-training is vital for systemic resilience. Because think about it. If you have only one person who knows how to operate the million-dollar filler, your entire factory is held hostage by that one person's immune system or their traffic commute.
Wow, yeah. If they call in sick, your constraint goes to zero.
You must cross-train to ensure critical nodes are never unmanned.
Another great low-tech solution they brought up, creating shadow boards for tools.
It is the simplest form of visual management.
Just a pegboard with the outline of the wrench painted on it.
Exactly. Everyone knows exactly where the wrench is, instantly. They don't spend 3 minutes rummaging through a toolbox. That is 3 minutes of non-value-added waste eliminated.
They also talked about staggering shifts for better coverage and minimizing movement by adjusting the floor layout so the most used inventory is literally within arm's reach of the operator.
It sounds so basic, right? But it is the fundamental blocking and tackling of operations. If everyone on the floor is performing the same unit process, you find the single person who does it with the least amount of wasted motion, and you standardize their exact physical mechanics across the entire workforce.
Just replicate the best person's movements.
Right. And you must pair that standardized training with rigorous tracking of your scrap rates
Why scrap rate specifically?
to uncover hidden waste. You need to ask, how stable is your overall manufacturing process? What is your process capability? Are you wasting 10% of your raw materials on scrap because of human error or poor machine calibration?
Oh, that makes sense. Someone in the threads actually suggested constantly reviewing the bill of materials, the BOM, just constantly looking for more reliable options for input materials. They said it is amazing what a single dollar does on the bottom line.
It is pure financial leverage. Think about the math. If you save $1 on a consumable component by finding a better supplier or reducing scrap, and you manufacture 1 million units a year
You just added $1 million straight to your bottom profit line.
without having to increase your sales by a single penny.
That's huge. The sources explored alternative waste solutions too. Like instead of constantly buying and throwing away cardboard boxes, which cost money to buy and money to dispose of, can you transition to collapsible, reusable plastic totes?
Right. Or can you take the physical waste your process generates, grind it up, or incinerate it, and use it to co-power your facility?
And to systematize all of this, the community highly recommended methodologies like Six Sigma. You don't need a building full of black belts, but getting your frontline managers certified as yellow belts or green belts gives them the statistical tools to identify and drive out variability.
They also champion semi-automation. You don't always need an articulated robotic arm. Sometimes, a simple $300 custom machined jig that holds a part perfectly steady while the human works on it will completely eliminate rework.
And drastically increase the speed of the unit process.
Absolutely. These are all highly accessible, profoundly effective ways to optimize the value-added unit process without breaking the bank. But here is the critical pivot, the moment of truth for any organization attempting this transformation.
Uh-oh, I feel a reality check coming.
If a factory has all these tools at their disposal, If they have mapped the floor with value stream mapping, if they understand the physics of deliberate constraints, if they've cross-trained their staff and built the shadow boards,
Right.
and they still fail to improve,
Mm.
or they still find themselves playing whack-a-mole, it is rarely a mechanical issue anymore. It is almost entirely an issue of culture.
This brings us to a fascinating dimension of the sources. We have to discuss how leadership culture impacts the persistence of recurring operational bottlenecks.
Because if bottleneck migration indicates anything beyond natural physics, it often indicates deeper systemic or cultural process failures at the management level.
Like, if you are constantly fighting the same fires, the problem isn't the fire. The problem is the arsonist.
And the arsonist might be sitting in the corner office.
Ouch. But so true. There was this profound point made in the source threads, originally posted in Italian. Let me pull it up. They said, I problemi derivano da persone e sistemi. Se hai sempre lo stesso problema, devi cambiare la mentalità prima, e poi di conseguenza persone o sistemi.
Which translates to, problems stem from people and systems. If you always have the same problem, you must change the mentality first, and then consequently people or systems.
And then they delivered the absolute hammer drop. Il collo di bottiglia potresti essere proprio tu, riflettici, meaning the bottleneck might be you. Reflect on it.
It is a harsh truth, but it is necessary medicine for any leader. If operational problems recur continuously, the ultimate root cause is the manager's failure to establish a culture of structured problem solving.
Yeah, if a manager reacts to a bottleneck by yelling, pointing fingers, or demanding faster work without changing the system, the bottleneck will simply hide, move, or return.
It takes a massive amount of ego swallowing for an executive to admit that their management style is the actual constraint on the factory floor.
Definitely. And quite often, instead of doing that painful internal reflection, leaders try to buy their way out of the problem by hiring external consultants.
Oh, yes.
Which leads us to the deeply cynical yet highly entertaining view of consultants presented by the manufacturing operators in our sources.
This is great. Let's return to our factory owner in China, the one with $20 million in revenue and a 25% profit margin.
Right, the guy printing cash.
He was genuinely wondering if he should drop $100,000 on a massive consulting firm like McKinsey to come in and figure out his operations for him.
The community's response was brutal and hilarious. One user, clearly speaking from painful experience, said, "In my experience, you're about to spend $40,000 on a diagram of your existing company that is slightly less thorough than one that any employee who has worked there for a year could draw on a napkin."
And it gets worse. They continued. After $160,000, you're going to get that list back as a PDF. But great news. It also have items you already tried after Googling the subject, and you already found out that they're not a good idea due to your specific, nuanced circumstances.
The overriding sentiment across the entire thread was that high-priced consultants are mostly there to interview your own employees. Write down what the frontline workers already know is the right thing to do, put it on fancy letterhead, and charge you a fortune.
It's often just a way for executives to cover their own behinds if a project goes sideways. Don't blame me, the board approved the McKinsey plan.
Another user offered what I think is the ultimate cynical consultant playbook. They said, take your organizational chart, remove 10% of the worker bees, remove 8 to 10% of the frontline supervisors, make the remaining people take on all the extra work, and take the $200,000 you would have paid the consultants and just put it in the overtime budget.
It's funny, but it highlights a very real, deep-seated frustration with top-down disconnected optimization. When people who have never run the machines are telling the people who run them every day how to be more efficient, culture breaks.
It totally breaks. And frankly, I have to push back on the factory owner a bit myself here.
Yeah.
If you are earning $4 to $5 million on $20 million in revenue, you have a massive golden goose. Why risk rocking the boat so violently with a corporate overhaul?
Several veteran continuous improvement engineers made that exact point. Continuous improvement is vital, yes. You must always seek to reduce waste. But you cannot kill the golden goose in pursuit of a theoretical ideal of optimization. If the organizational trauma of trying to squeeze out an extra 2% of profit margin breaks a functional, profitable culture, the juice is not worth the squeeze.
So if we strip away the expensive consultants and we move past the emotional gut feelings of management, we need a quick, objective way to measure reality before we start rearranging the factory floor.
Exactly. And this leads us to the final, highly practical component of our framework.
The 48-hour validation audit and transition metrics.
Yes.
How do we actually track our progress? What are the hard numbers we should be looking at when we are transitioning a factory away from whack-a-mole and toward deliberate constraints?
According to the operational science, you really only have 3 true metrics to track. As one user succinctly stated, you can increase throughput, you can decrease inventory, specifically by implementing Kanban pull systems, or you can decrease operating expenses.
That is the entire mathematical universe of
It
operations.
really is.
Let's explore those, especially Kanban, because we hear that word a lot. But I want to understand the physical mechanism of how it decreases inventory. What is a pull system?
To understand Kanban, you have to contrast it with how most factories operate, which is a push system. In a push system, machine A produces parts as fast as it can and pushes them down the line to machine B, regardless of whether machine B is ready for them.
Which creates that massive pile of WIP inventory, that trapped cash we talked about earlier.
Exactly, the localized optimization problem. Kanban, which originated in Japanese manufacturing inspired by supermarket restocking, flips this entirely into a pull system.
Okay, so how does a pull system work?
In a pull system, machine A is legally not allowed to produce a single part until machine B specifically asks for it.
How does machine B ask? Do they shout down the line?
Through a physical or digital signal, literally called a Kanban card. Imagine machine B has 2 small bins of parts in front of it. It pulls parts from bin 1. When bin 1 is completely empty, the operator takes the empty bin and the Kanban card attached to it and sends it back to machine A. That empty bin is the visual signal authorizing machine A to produce just enough parts to fill that specific bin.
And while machine A is filling bin 1, what is machine B doing?
Machine B keeps working, pulling from bin 2. It is a brilliant self-regulating loop. If machine B slows down, it empties the bins slower. Therefore, it sends fewer Kanban cards back to machine A.
Which means machine A is forced to slow down.
Yes, it physically prevents overproduction. It prevents the pile of trapped cash from ever forming.
And if machine A is forced to slow down and sit idle, that's actually okay, because as we learned, if it's not the constraint, we want it to sit idle.
Exactly. The pieces are fitting together. You decrease inventory with Kanban while simultaneously working to increase the throughput of your primary constraint.
And the third metric, decreasing operating expenses, is usually achieved by reducing headcount or cutting overhead. But as the sources caution, if you cut the wrong people, if you cut the cross-trained employees who provide resilience, you will inevitably reduce your overall output.
Absolutely. So how do we establish a baseline for these metrics without buying a massive enterprise software suite? Prasad Vaughn's framework provides a brilliant, elegant tool for frontline managers.
The 48-hour floor audit.
Yes, it is basically a checklist for frontline managers to identify and rank daily production issues.
Walk me through the mechanics of this audit. If I'm a manager listening to this, what exactly am I doing on Monday morning?
Monday morning, you take a clipboard and a stopwatch, and you go down to the floor. For 2 full working days, you or your operators conduct manual timing studies across all the major nodes in your process.
Okay, so I am simply measuring the maximum sustained capacity of each step under real-world, messy conditions.
Precisely. You time how many units the uprighter actually does in an hour, how many the filler does, how many the capper does. Let's say you compile the data and we convert it to minutes for easy math.
Sounds good.
The uprighter can do 40 units per minute.
Right.
The filler, your $1 million CapEx asset, can do 30 units per minute. The capper can do 45 units per minute.
Okay, I have my numbers now. What?
Vaughn provides a simple mathematical logic test. You input those node speeds. The physical system limit is strictly equal to the minimum value of those process nodes.
So the minimum value is 30, the filler.
Correct. The logic dictates that the constraint node is the one operating at that system limit. Your filler is the constraint.
But here's the critical part. What if the audit reveals a reality that management doesn't want to hear?
And that is the vital diagnostic insight of the 48-hour audit. If the identified slowest node is not your most expensive CapEx asset, your entire line requires immediate redimensioning.
Let me set up a hypothetical to make sure I grasp the gravity of this. I do the timing study, I analyze the data, and I find out that my $1 million filler is perfectly capable of doing 30 units a minute.
Okay.
But my cheap $50,000 upstream uprighter is only managing to output 25 units a minute because it's old and poorly maintained.
The math is unforgiving. Your system limit is 25. Your cheap uprighter is the system constraint. It is starving your $1 million asset of 5 units every single minute of every single day.
Wow. You are hemorrhaging potential revenue.
If we connect this back to the bigger picture, to the culture of an organization, this 48-hour manual audit stops the finger pointing.
It really does. It stops the emotional arguments in the boardroom about whose department is failing.
It provides objective, irrefutable, physics-based proof of where the constraint actually lives. It removes the ego. You aren't arguing about whether the maintenance team or the operators are at fault for low throughput.
You're just looking at the math.
The math says the uprighter is only doing 25. The filler is starving. The collusion is no longer a mystery. The solution is to over-dimension the uprighter immediately.
This has been an incredible breakdown. Let's recap the journey we've taken through these sources. We started by discarding the panic of whack-a-mole bottleneck fixing. We established that new choke points aren't managerial failures. They are the natural, mathematically inevitable physics of a continuous flow system.
From there, we examined the pervasive fallacy of localized optimization. We explored how incentivizing managers to make non-constraint machines run faster creates the illusion of productivity,
while actually causing severe capital leakage by building massive piles of WIP inventory trapped cash on the factory floor.
We outlined a framework. We talked about creating a value stream map to grant radical visibility, separating the true value-added unit process like turning a screw from the massive amounts of non-value added waste, like moving and waiting.
We highlighted the importance of cycle time analysis to identify the mathematical worst offender.
We then introduced the core paradigm shift, engineering the deliberate constraint. We learned the counterintuitive genius of the depreciation rule, intentionally overdimensioning cheap secondary assets to build buffers that fiercely protect the utilization rate of your highest depreciation asset.
We addressed the messy reality of human variability, the necessity of standardized training, cross-training, shadow boards, and tracking scrap rates to uncover hidden waste.
And we confronted the uncomfortable truth that sometimes the ultimate bottleneck is a leadership culture that relies on expensive consultants to tell them what their own employees already know.
And we finished with the 48-hour manual validation audit, a simple, objective way to measure throughput, implement Kanban, decrease inventory, and prove mathematically whether your most expensive assets are being starved by $50 sensors.
It truly is a masterclass in operations.
It is. But before we wrap up, I want to take this highly technical industrial framework and I want to pivot it entirely. I want to apply it away from the factory floor and into our own daily lives.
I think that is a fascinating application of the physics we've discussed today.
If we accept that intentionally running some factory machines below their maximum capacity is the absolute secret to total systemic efficiency, how might this exact same deliberate constraint physics apply to the human cognitive load in your own daily knowledge work?
Oh, that is a brilliant provocation. Let's explore that. Think about your own workday. What is your highest depreciation asset?
My highest appreciation asset.
What is the most valuable thing you bring to your company or to your own business? It is your brain. It is your deep, focused, highly creative, complex problem-solving time. That deep work is your million-dollar filler machine.
But we almost never treat our brains that way. We usually treat our brains like the cheap uprighter. We try to run at 100% capacity on low-value tasks.
We try to be the fastest person to reply to emails, the fastest person to respond on Slack, most efficient person at scheduling meetings.
We fall victim to personal, localized optimization. We optimize our non-constraints. You answer emails 15% faster, which, just like the factory machine, simply generates more replies.
Creating a giant, overwhelming pile of cognitive WIP inventory right in front of your actual deep work.
You starve your primary asset of time and energy to process administrative waste. That is huge.
So what happens to your personal productivity and your stress levels when you decide to intentionally overdimension your mundane administrative buffer tasks?
What happens when you deliberately schedule excess time for the small stuff or actively accept a lower efficiency like being slow to reply to non-urgent emails just to fiercely protect your most valuable deep thinking time?
You step out of the whack-a-mole game of modern work. You engineer a deliberate constraint in your own life. You ensure the primary asset, your mind, never starves and is never blocked by administrative jams.
It is a profound shift from trying to do everything perfectly to deliberately choosing what holds you back. The bottleneck might be you. Reflect on it. We'll catch you on the next deep dive.